ঠিক আছে, রাখছি।
Hello, everyone. Am I audible? Okay, great. I think we can wait for like 2-3 minutes more for others to join and then we can start today's session. Okay, I think it's already time now and we can get started. So, first of all, I would like to say a very warm welcome to everyone. Good morning, good afternoon, and good evening to all. As I understand, we have participants from across the globe. Uh, Thank you for everyone. Thank you to everyone for making the time to attend this webinar and making this event already a successful one. Um, and before we proceed, I would like to thank the members of AstroNova, first of all, for giving me the opportunity to host this event and most importantly for showing such enthusiasm and doing all the work behind the stage from creating posters, circulating mails, and whatnot. And I should actually introduce myself. I'm a graduate student at Kaptan Astronomical Institute, affiliated with University of Groningen, and I have been an alumni in the Department of Radio Physics and Electronics, University of Calcutta. Before we begin, I would like to say a few words about Astronova for those who are new here. So, Astronova is the astronomy club founded in 2022 by the students of the Institute of Radio Physics and Electronics, University of Calcutta, along with support from several IEEE societies at the University of Calcutta itself. Now, this society is for those who have a avid interest in astronomy in general. So usually we organize webinars, seminars, workshops like antenna designing, sky watching sessions, and competitions. All the events organized by the club are aimed towards the audience to stay updated with the recent trends. And today's event is also a part of the monthly webinar series where we invite eminent speakers to speak on the recent advances and opportunities in astronomy. And today, as our speaker, we have our very own Dr. Mayuri Rao from Raman Research Institute, Bangalore. I have been knowing Dr. Mayuri Rao for quite some time now. She is an amazing researcher and a very good human being. A little about Dr. Mayuri Rao. She is an engineer turned astronomer. She is currently an associate professor at Raman Research Institute, Bangalore. She obtained her PhD from Australian National University and did her postdoctoral fellowship at Lawrence Berkeley National Lab. She works in the area of experimental cosmology and builds custom radiometers to detect the most faint signals in the universe. She also works in the area of astrophysical foregrounds to cosmological signals. She enjoys reading and is an advocate of a healthy work life balance. Mayuri, once you're ready, the floor is yours.
Thank you, Sonia. Thanks a lot. I think I need permissions to. Okay, I think I can present now. Please let me know if you can see my screen.
Sure.
Are you able to see my screen?
Yes.
Okay, great. And how long do I have to cover the talk just to make sure I'm on time?
We are aiming for a 40 minutes talk, but
40
yeah, you
minutes.
can take your time. Yeah.
Okay, that's perfect. Great. Okay, so first of all, thank you everyone for showing up, and thanks a lot to the organizers for making this possible, and a special thanks to Sonia for her invitation. And we have a long association, like she said, and it's my absolute pleasure to talk to students from her alma mater. So, like Sonia said, I'm going to be talking a bit about my journey from going from engineering to studying the universe, and I'll be giving you some current research in the field that I'm working in, which and I'll give you a bit more about that in this talk. Like she said, I'm based out of Raman Research Institute in Bangalore, and here's a quick overview of my career journey. I completed my bachelor's in electronics and communication in 2010 from VTU in Bangalore, and I joined Raman Research Institute as a research associate right after my graduation in 2010. And while I was employed there, I got an opportunity to register for a PhD in astronomy and astrophysics at the Australian National University. and that is a 3-year program. And after completing my PhD, I moved to the US to Lawrence Berkeley National Lab for my postdoctoral fellowship until 2020. And I moved back to RRI as a scientist and was there from 2020 onwards. And while there, I was applying for faculty positions across India. And in a happy coincidence, I got an offer from Raman Research Institute as associate professor, where I'm currently a faculty. So here's a quick kind of globe-trotting timeline of whatever I've described so far. Now, a quick overview of my research. While most of you, I believe, are already members of this club, just a one line statement that astronomy is done at multiple wavelengths and frequencies. So, the traditional view of an astronomer looking through the eyepiece of a telescope is no longer the current modern view of what an astronomer does. And I specifically work on experiments that try to understand the universe at radio frequencies and also now at submillimeter frequencies. Okay, so that's a higher frequency or shorter wavelength. Now, the kinds of research areas that I work on include studying the cosmic microwave background radiation. I'll give you a quick introduction to that in a following slide. And specifically in the cosmic microwave background radiation, I work to study the spectral distortions in this radiation. So that includes scientific goals of studying how and when the first atoms formed in the universe over what is known as the epoch of recombination, how and when the first stars and galaxies in the universe formed, which is a period collectively known as cosmic dawn and epoch of deionization. Apart from this, I've also worked on experiments that try to answer this question of what is known as inflation, which is an open problem in cosmology. And for that, I've worked on experiments that study the polarization of this cosmic microwave background. And like Sonia mentioned, the other thing that I truly enjoy is studying astrophysical radio foregrounds to these cosmological signals. I've used a lot of jargon here, so I'll quickly jump into giving you a bit more introduction to some of these areas before I go into some details on one of the experiments. Okay, so what is cosmology per se? Cosmology is different from astronomy in that it involves a study of the universe as a whole. So its history, evolution, composition. So we're not studying a specific star or galaxy or an object, but the entire universe is the object of study. So if you think of our universe timeline as a calendar, and you think that the moment our clock starts ticking when we think the universe started is the midnight of January of the year, then where we are today is literally the end of the calendar year. So 31st December, just before midnight of the next year. Okay, and we are trying to look further and further back in time to the periods when the first stars formed, which is sometime around the February in that calendar, and when the first atoms formed, which is mid-January in that calendar. So sitting where we are now in the present timeline in the universe, we are trying to understand the universe as it was way back when, very close to when it formed. Okay, and just to cover the picture, this timeline in our understanding of the universe spans about 13.8 billion years. Okay, now the current model of the universe that is accepted, more or less, is known as the lambda CDM model. You might have heard of this popularly called as the Big Bang model. A way to think about it is that we have from observations experimental evidence that the universe is expanding. Now let's reverse this and keep going back further and further back in time. Everything in the universe, all the galaxies, everything were closer and closer together until you get to a point when everything is so tightly packed and so dense that it is extremely hot. Okay, and eventually you will get to a point which is a singularity. Okay, we don't quite understand what happens to trigger off this point, but at that point the universe starts existing. Okay, and that is what we popularly call the Big Bang. Okay, and a very quick overview. Let's say we have the clock started at this Big Bang. We do believe, there is reason to believe that we think there is a very rapid period of expansion of this universe, and that is called as inflation. We don't quite understand what triggered it, if it really happened, if so, what drove this inflation. All of these are open problems. But we do know that within the first few minutes of the existence of the universe, all the matter that you and I are made up of, everything that we understand as matter, existed as a plasma or a very hot soup of protons, electrons, and some helium nuclei, along with radiation. Okay, that was released in this process of what we call as popularly the Big Bang. Gradually, the universe expands and cools down, and the first atoms formed. Okay, so an electron combines with a proton and forms a hydrogen atom. That is the first atom that forms, and then some helium atoms. Eventually, the first stars and galaxies form, and the radiation that these stars and galaxies emit convert that hydrogen atom back into protons and electrons. Okay, and the radiation that was released in the very early universe, which was bouncing off of the plasma, the protons and electrons, eventually escapes and reaches us today. And if you observe this radiation and you try to make a very precise measurement of the intensity of this radiation as a function of frequency, you will realize that it very beautifully follows a curve of a black body with a temperature of about 2.7 Kelvin, and that peaks in the microwave region of the electromagnetic spectrum. This is what we call as the cosmic microwave background. So all of this is a quick overview of what has happened. But there remain several open problems. I've said this story like we've figured it all out, but clearly we have not. We Here are some of these questions we are trying to answer. Do we understand the physics in the conditions of the early universe when this inflation is supposed to have happened? When did the first atoms and stars and galaxies truly form? How did they behave? What kind of radiation did they emit? Is there any other exotic matter or physics out there we have not captured in our understanding of the universe? All of these are questions that we are trying to answer, and people use different techniques, different wavelengths, etc. But for the purpose of this talk, we will specifically focus on very faint radio signals that we are trying to detect, which will help us answer some of these questions. Okay, now today's talk I'll focus on one experiment, which is trying to answer this question of when the first galaxies formed, how did they form, etc. And for that, the probe that we will use to study the universe is the hydrogen atom itself. Okay, so hydrogen is the most abundant element in the universe. So if you do a quick recap of your understanding of basic physics, what is a hydrogen atom? Essentially, it's a proton and an electron. Now, because of quantum states, this proton and electron can coexist in two different manners. One with their spin aligned to one another, the other is their spin anti-aligned. Okay, and the anti-aligned state is a more favorable energy state. So when our hydrogen atom flips its state from being aligned to anti-aligned, there is a small energy difference between these two states, between these two atoms, and that energy difference corresponds to a photon of frequency of 1420 megahertz or a wavelength of 21 centimeter. This is a very rare transition. It has a transition rate of about 10 raised to minus 15 seconds inverse. But just because there is so much hydrogen in the universe, it's a very powerful or useful signal to try to detect. So what we try to do is, if you want to detect this signal or you want to study hydrogen from further and further back in the universe, we use a principle of what is called as cosmological redshifting. You all know as Doppler shifting. You've all heard of this. Uh, Similar to that, but different underlying physics. This frequency gets shifted to lower and lower frequencies or longer wavelengths the further back in time we try to detect it. Okay, so by trying to detect the signal from about 40 to 200 megahertz, we believe we will be able to study the universe in that state or in that age when the first stars and galaxies should have formed. This period is known as the cosmic dawn, and epoch of reionization is another period that follows. So if you take an antenna, if you build a nice experiment, you take an antenna, you connect it to a receiver, and you try to measure what you will see at this frequency range. And let's say you don't have any radio frequency interference, you don't have your FM 94.3 or whatever, you just make a very clean measurement somewhere. This is what you will see. On the y-axis is temperature. Temperature is a proxy of, let's say, intensity or energy, and on the y-x-axis it's the frequency. The temperature scale goes to about a few hundred Kelvin, could go to 1,000 Kelvin even. Okay, what is this that we are seeing? Is this the signal from the early universe? The answer is no. What you are seeing at this frequency is actually radiation from our own galaxy. Remember that any observation we make to study the early universe, way back when, you always have to look through our own galaxy to look further back or to look further out. Okay, and it so happens that our galaxy is very radio bright. There are electrons from, cosmic ray electrons that are getting accelerated along some magnetic field lines in the universe, and this is a very highly relativistic process, and it emits um, very bright, very intense radiation at as you go to lower and lower frequencies. While this is the signal from our own galaxy, the signal you want to detect is the one that is in red color in this figure. Okay, so the blue signal was the radiation from our own galaxy. For this talk, we'll call it foreground. Okay, and if you see the red curve with the different y-axis, it's in the order of magnitude of tens of millikelvin. Okay, whereas the foreground is 1,000 Kelvin or so, and it's a very very weak signal that you're trying to detect, and this is a fundamental challenge to see detecting this signal. Okay, now we can get into more about why the signal is of this shape, what parameters determine this, etc., in the question and answer session if you're interested. But let's say this is the kind of signal you want to detect. Fine, you can design a very nice experiment, try to detect the signal, etc., but you don't know what the signal truly looks like. While I showed you this red line, uh, this is just one of the many, many variations of the true signal of hydrogen from this cosmic dawn and epoch of reionization. The specific shape, amplitude, intensity, turning points of the signal are all determined by things like, when the first stars and galaxies formed, how did they emit radiation, how much did that radiation heat up the gas around it, etc. So if you go out and find the true signal in this forest of signals, you can work backwards and answer those questions. You can detect the signal, look at its shape, and say, oh, this signal means first stars formed at this point in time. The kind of radiation they emitted was like this, and that's how you detect the information. So, for those of you who have any interest in information theory, the more the these unknown parameters you're able to constrain, the more information you're going to get out of this problem. And hunting for this very very weak signal in the presence of these bright foregrounds is the kind of work that we in our lab do at Raman Research Institute. uh, this signal has never been detected before. It is a cutting edge problem. There are several groups in the world trying to work on this problem, and I'm happy to say that our group at Raman Research Institute is the leading group in the world in this area. So, how do we do these measurements, right? Um, Fundamental experiment design is very simple. You have an antenna, you have some analog electronics it is connected to some digital electronics, you have some mode of calibrating this entire system, and the data that comes out, you do some analysis and processing. It all sounds very simple, but it's a very challenging experiment, and I'm going to tell you why. So one part we've covered is the foreground is very tricky. It's very bright. We don't understand the signal very well. So how do you separate? And you're trying to find a needle in a haystack, and you don't know what the needle looks like. Okay, that's the challenge. But in addition to this, to go and measure a signal that is 10 millikelvin in a foreground that is 1,000 Kelvin, you have to make sure that your own instrument, your own experiment does not do anything to contaminate um, the signal you're trying to detect. So you want to retain purity in your dynamic range of your instrument behavior, all the way from wherever it is performing down to 1 part in a million. And that is extremely challenging. And to top it all off, if you remember what I said a few slides ago, this frequency range of this experiment is also exactly where we have a lot of radio frequency interference, primarily from FM transmitters. So let's look at this in a different point of view. You have an antenna, you have the receivers, you have your data. Everything that is highlighted in pink are all experiment related challenges that you will struggle with anywhere you perform this experiment. Okay, that's got to do with the fundamental nature of the challenge of the experiment itself. But in addition to this, the ones highlighted in blue are challenges that you will face uniquely if you're making a ground based, earth, soil, ground based experiment. Okay, and what is that? It is radio frequency interference, like I mentioned. You also have effects of the ionosphere. Our own ionosphere that you look through if you're observing from earth can scatter, refract, reflect, and just change the signal a bit, and that's tricky. And you have to understand these effects to 1 part in a million. And the third part is that you have an experiment that is, say, sensitive to 1 part in a million to what comes from the sky. It is also equally sensitive to everything in its environment. So if you have an antenna that is connected to electronics and it's so sensitive, it will also pick up things like rocks and shrubs and bushes in its environment. And that's a big challenge. You can overcome all of these challenges if you go and put an experiment in the far side of the moon. So that is the side of the moon that you never see. Okay. And if you have, in particular, not just a lander, but if you have an orbiter that goes around the moon and makes scientific observations when it is in the far side, you address all three of the problems that I mentioned. No ionosphere because, well, you're behind the moon in orbit. No coupling to the local environment because you're not on soil, you are literally in free space. And more importantly, no terrestrial RFI because the moon, it has been shown from some previous experiments and simulations, is believed to be a very good attenuator of radio frequency signals. So while you go to the near side of the moon, the side of the moon you see, you will still pick up FM. But as those radio signals not able to penetrate through the, you know, lunar regolith and the lunar structure, the far side of the moon is very radio quiet. So we have done just that. We have placed a proposal to ISRO for an experiment called Pratush, which stands for Probing Reionization of the Universe using Signal from Hydrogen. In its full glory, Pratush will operate from 40 to 200 megahertz, but the baseline design I'm presenting to you today operates from 55 to 110 megahertz. It will be a custom lunar orbiter experiment uh, with the primary science goal of detecting this very faint signal from the cosmic dawn to help us understand the formation of the first stars and galaxies. Our counterpart ground based experiment called Saras 3 has made a splash recently, relatively recently, a couple of years ago now, and in the news. You can go look it up. It's a very exciting and interesting experiment, but it's a ground based experiment. So, Pratush will be its space based counterpart. And after completing 2 years in a seed funding stage, Pratush has been recommended by the technical committee of ISRO to move to project mode. And we are currently working on getting to that project mode phase. So here's a artist visualization of what Pratush will look like when it is making scientific observations. You have the earth and the sun and the moon. And when the Pratush experiment is on the far side in the shadow of both the earth and the sun, it will make its scientific observations. When it orbits around the moon and comes in line of sight of the earth, it will transmit the data back to the ground station for further analysis. So here is the Pratush experiment concept. You have a antenna, which is the gray stuff here, which is sitting right on top of electronics. And the electronics include both payload electronics as well as spacecraft electronics. So you will note that the antenna is not a conventional antenna. It's not a dipole, it is not a parabola. It's a very interesting shaped antenna. And that is for a reason. It is a custom designed antenna to operate over a chunk of metal, which is basically the satellite bus, which preserves the shapes of the signal you are trying to detect. You don't want your antenna to introduce any funny shapes that will confuse the signal detection. So it is custom designed for that reason. So here is the current status. We have a laboratory or an engineering model undergoing testing in our lab at the Raman Research Institute, and few more nice pictures to just show you some details. So for scale, that's a normal length human adult standing next to the antenna. So the antenna is almost 1.5 meters tall, and here are some electronics. So this is the digital electronics opened up, and the analog electronics is inside this box here. Now, here are some more slides. I won't go into too much detail for the sake of time, but like I was mentioning, we put a lot of effort into designing our antenna because the antenna is the first sensing element that you see, right? So you have the signal coming in, the electromagnetic or the RF signal gets converted from an EM wave to a voltage by the antenna. So for those of you who are familiar with this terminology, you don't want the transfer function of the antenna to distort the very signal you're trying to detect. If you do that, you're doomed because you have kind of perturbed and muddied the waters, and you're trying to find something very faint in that. So we want to maintain few properties of the antenna which are important to us. Broadly, we call this chromaticity. Chromaticity is a way of describing the change in the property of the signal as a function of frequency. So antenna has two primary properties. It has a beam, which you may have an intuition for. It is basically the sensing pattern of the antenna. And since the experiment operates from 55 to 110 megahertz, you want to make sure that the beam is stable as much as possible between 55 to 110 megahertz. The other property is what we call as the return loss of the antenna, which is how that voltage at the antenna terminal goes into the cable that connects to it and into the receiver. You don't want things bouncing around there back and forth, creating standing waves and ripples. So that's a coupling function between the antenna and the electronics. So we pay a lot of attention to make sure that the antenna beam and the return loss don't introduce unnecessary chromaticity. And we do this using EM solver software. We use something called CST Design Suite. We have something called FACO. These are all EM tools. And those of you who are doing, this kind of work in your courses, if you're doing antenna engineering, these have real life application in astronomy along these lines. Okay. And we also do a lot of coding. We do a lot of extensive coding, and just one example of the output of the code is given here, where we simulate a sky spectrum, we put it through the antenna, we correct for the antenna response, we put in all the cosmological signals that may be present into that model, and we try to detect this signal present back. Okay, and that helps us qualify whether the antenna is suitable or not, and we do this iteratively for a long period of time. So that is how we kind of finalize our antenna design. Then we have the analog receiver. It is a very nice, highly calibratable, beautiful RF receiver. Those of you who are studying this part of engineering, you will see familiar components like you have low noise amplifiers, you have phase switches, you have attenuators, you have noise sources, you have filters, right? And you again pay as much attention to detail to the choice of every single component. And this receiver serves primarily three functions. Okay, if you're able to see my mouse, the left half of this block diagram panel is what we call as a vector network analyzer. You may have worked with a vector network analyzer on the bench top in your college lab. For those of you who are not familiar, it is a machine or a test and measurement instrument which does a comprehensive analysis of a radio frequency device. In our case, our antenna is a one port device. Since we can't fly a commercial vector network analyzer in space for Pratush, we are building a high precision custom VNA from first principles, just from fundamental operations. And that is what this left half of this block diagram is. And what that will do is it will measure this return loss of the antenna in space. And why this is important is because remember, as your antenna and your experiment is orbiting the moon, it will see the sun for some time, go into a very cold region, come back and see the sun, hot region. So it's going to undergo a lot of thermal fluctuations. And when you expose a metal to thermal fluctuations or thermal cycling, it will distort in its shape. And an antenna is just a piece of metal at the end of the day. And if you change the shape of the antenna, all that effort you've put into designing the antenna has gone to waste, because it is no longer the antenna you designed and launched to space. So we constantly will be monitoring the property of the antenna using this VNA. And the right side is the rest of the RF receiver, which does two things. It takes the scientific signal from the antenna and calibrates it, which is, it tells us if you get the output of this signal to be some units, you want to convert that back to meaningful units and remove all the shape of these amplifiers, etc., in that chain. So that is what calibration is in our context. So you want to calibrate the signal, and you want to kind of amplify, filter, do all those basic functions to make sure the signal has enough strength to be processed by the rest of the electronics. So that is the right half. The digital receiver does two things. It samples the analog voltage signals coming in, and it takes a Fourier transform of the signal. So those of you who are studying Fourier transforms and wondering when will I ever use this, I want to study astrophysics, it is probably the most useful concept you will encounter, especially if you're interested in radio astronomy. It is used in so many ways, in so many applications. You will be amazed. So please enjoy your signals and systems courses, your digital signal processing courses. They're highly relevant and directly applicable to astrophysics. Okay, so you take this Fourier transform and then it goes into a computer. And then from the computer, it goes to your satellite bus, and it is eventually downlinked, like I mentioned. Okay, now here is a quick current timeline overview of where this field stands. On the left, uh, is a whole range of signals that have been predicted, and everything in maroon has already been ruled out by the Saras experiment, which is the other experiment in our lab. Everything in gray, which is basically looks like it's just filled in, but every single thing there is a separate line, uh, is still open, right? It's still a viable candidate for the model for cosmic dawn and reionization. So we will zoom in on this gray area and look here on the right panel. If we put Pratush, okay, initially in Earth orbit as a low Earth orbiter experiment, we will be able to constrain every signal that is in blue. So if one of those blue models is the true model, Pratush, just by virtue of being somewhere above the ionosphere and not coupled to the soil, even though it will see RFI, it is not coupled to all the terrestrial other artifacts. We will be able to we will be sensitive to all these blue signals. So if any of these blue signals is the true model of cosmic dawn, we will be able to detect it, and that will be a first detection in the world. Okay, however, if it is any of the red signals, then we'll have to go to the lunar far side. So naturally, if you go to the lunar far side, you're sensitive to both the red and the blue. But let's say we have a launch window, we are able to go to low Earth orbit in the near timeline, we will be sensitive to the blue signals. So how do we know this? Like, we need to first thing we need to answer is, let's say I do this experiment in low Earth orbit. It is less expensive, it is less complicated, you have many more launch opportunities. So why not do low Earth orbit? The reason is terrestrial radio frequency interference, primarily from FM transmitters. So we decided, let's go ahead and try to understand how much FM our experiment will see in space around Earth. And this is not a known problem. So we try to answer that problem. And that is where Sonia's work comes into the picture. So Sonia, after her graduation, joined our group at Raman Research Institute. And it was an absolute pleasure working with her. And it is unsurprising she got an excellent PhD position with Groningen. So what she did is she took a limited database of FM transmitters from across the world, from different countries, and wrote the code to do the appropriate calculations to make some maps like this, okay, or to make some spectra like this. So if you are at different altitudes over different locations on Earth, and your antenna could have whatever beam pattern you input, how much FM will it see? How much power as a function of frequency will it see? For example, in this plot. Or if you're at different locations, at different frequencies and at different altitudes, how does this a colored heat map of FM transmission change? Okay. There are a lot of dark blue patches in some of these maps because our transmitter database was limited. And currently, Sonia and I, along with my colleague Saurabh Singh, are working with another student in our lab to fill this database and give a more complete picture. So, this kind of code will tell us if we have to go in a low Earth orbit, what are the orbital parameters we need to choose? Where should we be observing our sine signal, and where should we be turning off our instruments because FM is too high? And that's the kind of work that Sonia's project has helped us answer. So, just to give you a quick general picture, right? We spoke about this 21 centimeter signal from hydrogen and how studying that signal from the early universe can help us understand the early universe. Okay, and what kind of ongoing work is there in our lab, specifically with an upcoming lunar orbiter experiment, Pratush, that we have proposed. So, just for your understanding, your conception of what an astronomer does, I hope I moved that needle by a bit. And this is the kind of work an astronomer does, right? We are in the lab, we are building experiments, we are writing codes, we go to the field to deploy these instruments that we build. We work with other engineers on different aspects of either antenna design or digital and analog receiver design. We write our own algorithms to analyze the data and how to understand which is the true signal, what is the physics determining the signal, how do you separate that from the foregrounds. And that's what an astronomer like me does. And just to kind of close off, here are some things that we also do. Other than being in the lab, you spend a couple of years or a year in the lab building instruments. Then we go out. For example, a few months ago in August, I was in Ladakh with the rest of the team. We went out and deployed some of these experiments, made some measurements, and came back. And now we're going to spend some time analyzing that data. So this is just a picture of one of the sites we were, several thousand feet above sea level making these measurements. So yeah, so motivation of the story in terms of your applicability to engineering students is that you will be learning a lot of skills as an engineer that you will apply to astronomy if that is the direction you want to go. So don't be in a mindset that this is not astronomy what I'm doing, but I want to do astronomy. Every single course you are taking will have a connection to astrophysics. So work with a lot of curiosity, and there is a lot of difference between studying something in theory but get experience with projects so that you know how it is in practice, and try to let that be your motivation to get into astrophysics if that is what you want to do for your PhD, for example. And I'm literally listing out, I don't want to read this list out. I'm listing out a bunch of the courses that I studied in my engineering degree that I am applying on a day to day basis as a practicing astronomer. Okay. So look through that, and I'm sure there are some courses that may be familiar to you that you may not have thought have an application to astrophysics, but it does. Okay. And some kind of unsolicited advice because I have your attention is, again, work with curiosity, learn, understand, apply everything you learn, and go and seek out opportunities to work in this field with astronomers. And even if it's not a what even if it does not sound like an astrophysics project, it could be an engineering project, but it is relevant. So get that experience. Don't be afraid to ask questions, go deeper in your understanding. And especially those of you who want to apply to go to the US, for example, GRE is not your biggest kind of determinant of whether you get the seat or not. GRE just gets you through the door from the admissions office to the department. What gets you the PhD position is your experience from your final year project, from your break year. So make that count. And yeah, keep in touch with your peers, your alumni, your mentors and teachers, because they will be writing your application, your reference letters. and they count for a lot. And yeah, make the most of your time in your college. So yeah, I'll end with that. I think I am kind of sort of in time. And I have a small blog. I mainly want to point you to the resources section there, where you can go and look up more materials relating to astronomy, the kind of work we do, and just some general fun stuff, including a small blog. There's one particular link that takes you, talks more about going from engineering to astronomy. And last thing I want to add is that at the Raman Research Institute, we have what is called as a visiting student program. It is a very competitive program where we get applications from students. So if you are interested in this, uh, it's like an internship. It's a paid internship. You'll get some minimal pay, but it counts for a lot on your CV. It need not be just with me or our group, but anyone at RRI, in the physics areas you want to work on. You can go look up the website, write to the individual you are interested in working with. Please make it a nice email, introduce yourself, attach your CV, mention when to when you want to do a project, and you may get a call back from someone saying, let's have a chat, and you may have an interview and you can get an offer. That is the process. There also is like a list somewhere on the RRI website that kind of gives you more information about this. So if you're interested, I encourage you to go look this up and contact whoever you would like to work with. I think, yeah, that's the end of my talk. I'll be happy to take any questions. I think I'm on time.
Yes, Mary, you are just perfectly on time. That was really, really incredibly inspiring. As always, I have always loved to hear your talk, and you never fail to disappoint.
Thank you, Sonia. Thank you so much.
So, we are ready to take some questions. I think are already few on the chat. Um, Maybe we can start from there. And from the audience, you can maybe raise your hand and unmute yourself. Yeah. Okay, so the first question from the chat we have is from Pallav. He's asking, normally when we talk about the radio receivers, we talk about the power in dBm, like the sensitivity of a mobile phone is minus 120 dBm. Could you please tell how to link dBm to the temperature Kelvin as shown by the graphs in the talk?
That's a great question. I'm glad you asked that. So there is a standard formula that we use to go from power to temperature in radio astronomy in general. So which is power P is equal to K, which is your Boltzmann constant, times equivalent temperature T times bandwidth B. Okay, P is equal to KTB. So if you, and that will give you, if you use SI units throughout, you will get the power out in watts. And of course, I'm sure you know how to go from watts to uh, dBm. Interestingly, the signal we are trying to find is in the range of about, again, similar minus 120 or minus whatever, sub 120, minus 120 dBm. It's really faint. But like I said, there are two aspects of this challenge. Why can't I just go out and use a nice, great, fancy mobile phone to detect this? Well, few reasons. First of all, you need a very wide band observation. You need a calibratable observation to be and to be able to separate your receiver induced systematics from the signal, and you need to be able to make this sensitive measurement across the whole band of several octaves, 40 to 200 megahertz, while um, retaining the shape of the signal true to its form. So you need to build a very fancy custom wideband experiment like Saras or Pratush.
Thank you, Mary. So Pallav also has another question, that is why monochrome antenna only? Gain, polarization, reflection coefficient. Uh, how much is that important?
Yeah. So there are two aspects of this problem. Why monopole? Well, we had worked on dipole experiments before in our lab. Um, there is nothing sacred about a monopole antenna. We There are trade-offs between both using a dipole and monopole. For example, in a dipole, you'll have to do two things. You have to have a ground plane below your dipole antenna, just because the way you want the radiation pattern to look up. So once you put a ground plane below a dipole, you will have other standing wave reflections between this dipole and the ground plane to 1 part in a million easily. And secondly, to go from a dipole to a say connector, you either need to use a differential amplifier or a balun, and they are also inherently chromatic. So you either have to deal with all the other nice properties of a dipole, but you have to live with these problems, or you go to a monopole antenna or monopole antenna, which has other problems, but you don't need a balun. You have a shaped profile ground plane that is the funny structure you see below. That is the main reason. We are sticking to monopole just for that reason, from experience of working with dipole and finding them very tricky. The polarization part, the signal itself is intrinsically unpolarized, so we are not really losing much. We are just losing half the power, but that's okay because our signal is unpolarized, so that doesn't matter.
Thank you. So, final question from Pallav is: as a PhD student, can we apply as visiting student?
I have never seen that happen. The better format to go is to get your advisor to talk to someone and have a collaborative project. But typically, no, because well, you will be getting stipend as a PhD student, and the BSP program is meant for undergrads and break year students. So if you want to work as a PhD student with our group, it has to be more through more formal channels between advisors and university RRI, like that.
Okay. We have next question from Amlan in the chat. How much role does machine learning algorithms play for signal processing and data analysis?
Plenty actually. In fact, I know at least 2 or 3 students just in one university, IIT Indore, who have got their PhDs from machine learning algorithm application to this problem. Okay, so yes, the answer is very much, and it can be used in the area of predicting the signal shape from cosmology, detecting the signal out of programs from data. So there are many applications.
We have some raised hands. So, Pratik, maybe you can go ahead and unmute yourself.
Thank you so much. That was an amazing talk, ma'am.
Thank you.
I want to ask you that you said the far side of the moon was chosen for Piyush. So why not the Lagrange point L2 was chosen?
Well, L2 still sees quite a bit of the sun. So remember, if you are behind the moon, you also want to be not too far behind, because I'll try to go back to a slide. The the intensity of how radio quiet, or rather the darker this shaded region is behind the moon, the more radio quiet it is. And that falls off if you go further and further beyond the moon. That's precisely why. So ideally, there are experiments that have been planned that land on the far side of the moon. I know Sonia is working on one of those. And that is the most radio quiet you will get. But we are in orbit, but we want to be close to, but not on the lunar surface, just because it is more radio quiet there.
Yeah, ma'am. I also wanted to ask. I'm currently a third year undergraduate student studying in Ferguson College, Pune, and I'm doing some sort of small radio project like with the ASRT, Affordable Small Radio Telescope, just monitoring solar transients. And I feel quite a lot complicated with the electronics. Like you have suggested for the electronics guys regarding astrophysics. So, what would you suggest me regarding electronics?
So you are from astrophysics or physics background, is it?
Yeah,
Okay. Um, I don't know if there's something that I can tell you right now on the Zoom call that will solve your kind of general question, but
yeah.
try to get experience in labs that do have engineers so that you can start working with them. In fact, many VSPs we do get in our lab have physics background, but they are hobby electronics people. So yeah, fiddle around, play with your Arduinos and play with your SDRs. It is by practice, but for formal things, yeah, take courses when you can in electronics departments. Work
Mhm.
with people who do have hands-on engineering experience. Uh, it will build up with time, but yeah, for specific, I think it's hard if you go to one person with one specific question. Hey, I'm stuck in this part, help me. They may not understand your bigger picture problem, so start working on projects with people who do have an engineering background.
Thank you so much, ma'am.
I think the next person is Unikrishnan. Maybe you can
Hi, thanks a lot for the great talk. The work is very interesting. Can you move forward to the plot where you showed how Leo constrains a model in a different way?
Sorry, there are a lot of crackers going off here. I didn't catch which slide you want me to go to.
The one that showed how Leo uh, kind of constrains the
Oh,
thing in a different way than
sure.
perception.
Yeah. This one, right?
Yeah, yeah, here. So I have two questions here.
Yeah,
One thing, how many parameters are you trying to constrain in these models?
yeah.
And the second question is, why the Leo and the lunar orbit, they like, why are they different in this case? How are they different? Because if it's something like some parameters are mostly affected by the radio interference than others, or why do we see such a difference?
Yeah. So first question is typically, I mean, it is based on what kind of analytical form you are fitting to. So if it is astrophysical and cosmological parameters, there are typically five or six of them, including something like rate of star formation, X-ray efficiency, size of the dark matter halo into which your stars collapse, etc. So that those are about six derived parameters. But just from a
Mm-hmm.
signal point of view, if you want to fit to the shape as an analytical form, we use just a Gaussian. So very few parameters. Okay, just the central, the mean and the standard deviation of the Gaussian is all, and an amplitude. So three parameters. Coming to the second part, um, okay, so just to clarify, once you fit to those first three parameters, then you can get to the other five or six derived astrophysical parameters from the theory models. Now, the right side plot, the blue Leo, even though it covers the entire 40 to 200 megahertz, actually what we have done is assume that we have zero information about signals above 88 megahertz. So assume that you have lost your entire FM band, 88 to 108 megahertz, and all the way 88 to 200 megahertz. Even if you have no information about that, you will notice that all of these signals have a certain kind of a very strong, sharp turning points in the lower frequency range. And our algorithm is sensitive to picking out those sharp signals that have a turning point in this lower band. So that is the Leo. Lunar, we assume we have full sensitivity from 40 to 200, so no FM, no RFI at all. The, so these are the other signals which we are able to constrain if we use the full band, and that is the difference between the Leo and lunar prediction.
Okay, okay. Thanks a lot.
Yeah.
I think we have the last 4 minutes. I see Sankit's hand raised. You can unmute yourself, Sankit.
Okay, so thank you, ma'am, for your beautiful talk. Uh, I have one question about in your slide. You have mentioned a frequency-dependent beam in an
Yeah.
antenna. Yes. What is this frequency-dependent beam?
Oh, so remember that your antenna is operating over a wide frequency range. It is not at one frequency. Most antennas, including your mobile antenna or your TV antenna, FM antenna, is very narrow band. But we are trying to go from 55 to 110 megahertz. So kind of an octave, double range. And in this range, your antenna beam needs to be as stable as possible. It needs to look in pattern the same way at every single frequency. It means independent of the frequency at which you're seeing. It has to have the same property. And that is what we call a frequency independent antenna.
Okay. Thank you, ma'am, for that. And I have another question that you have mentioned about some electronic components
Mhm,
like for filters, LNAs, and etc.
mhm.
But can you just detail a bit about the digital signal processing section because that's a very difficult section.
Yeah.
And
So what we use an FPGA based receiver. Right now, what we have in our lab for a ground based electronics is from Xilinx. It's a Vertex 6, I believe we're using. Um, and we are moving on from this to an RF SoC, so RF system on chip based uh, board, for example. We have the fundamental building blocks are basically analog to digital converters. We use two of them. We have 10-bit ADCs right now, but we will be moving to 14-bit ADCs shortly. The sample, because the signal we are going to about 110 megahertz as the upper limit, we try to at least oversample by a factor of 2 because of Nyquist theorem. So we go to 500 megahertz or 250 megahertz sampling. 500 megahertz for the ground-based experiments is just easier. For space-based, we have to be more conservative, so we go to 50 megahertz sampling. And yeah, ADC is connected to the vertex chip, and that's where all the magic happens. That's where the Fourier transforming, multiplication, etc. happens, and then that is connected to memory. Beyond that, all your monitor and control in the ground-based experiment comes from a laptop. But for our space-based experiment, we have moved everything to a single board computer. Right now, it's a Raspberry Pi, but it will move to a space-qualified SBC in the future. And beyond this, you have other monitoring control signals, power supply, memory, etc. And I should mention that the boards that we are using in our lab have been custom designed and built at RRI. We call them P-spec boards, precision spectrometer boards, and that is the current version we are using. We are in the process of building the next generation digital boards, which will be based on RFSoC based electronics.
Okay, thank you.
Yeah,
Mayuri, I think it's already 8:30, but if you like 5 more minutes to speak, then we can just take two more questions.
sure, that's fine.
Okay, Mahendra, you can unmute yourself.
Hello, ma'am. Thank you for the wonderful presentation. My question is, in the RF chain, you have power amplifier, you have mixer.
Hmm.
Okay, and when you connect power amplifier, the power amplifier throws up lots of nonlinearities, and when you're going for high power, you end up getting the nonlinearities in the in-band region where you have message as well as many harmonics and spurions and many intermod products. So how well are you fine tuning and removing that so that you can get your message signal?
Yeah. So that's a great question. First of all, we try to avoid any high power coming in. You will realize that all of our signals are very, very weak, including our galactic noise. It's very weak. So to make sure we operate in the linear regime, we do a few things. First of all, the power amplifier comes a little down the chain. The first element is actually a low noise amplifier, and the gain of that low noise amplifier and its noise temperature is very carefully chosen such that that will dominate the system temperature, the receiver noise temperature, and any other feedback that goes on further down the chain. We put an upper limit on the tolerable um, specs of what the IIP3 is, what the intermod products are allowed, etc. But finally, like you said, you're absolutely right. Everything is determined by how much power you are pumping into the input of these amplifiers, which is why we have to make sure that we are operating at the correct power level of the sky signal. We avoid sites with very bright RFI, so we don't operate in cities. We go to very, very remote places like Ladakh where we don't get any FM connection, etc. And we are dominated by the sky noise. And the rest of the electronics chain is designed to operate in a linear regime. Every component, including LNA, power amplifier, everything else, is designed to operate in a linear regime for the sky power under various conditions with some buffer. So you do always have some tolerance built in. For example, if your galaxy center or galactic plane is in your antenna beam, you will see higher power. When it is off galactic plane, you will see low power. So all of that is built in. We avoid operating during the day also because even the sun can be very radio bright. So we factor all of that in and pick our components. We never pump in high power ever.
I hope that answers your question, Mahendra. So we
Thank you,
can,
ma'am. Thank you so much. Yes.
thanks. Arjun, you can unmute yourself. Arjun, are you there? that he is facing some issues. Okay, he is back. Can you unmute yourself? Okay. I think he is facing some issues. Okay, in that case, Mayuri, once again, thank you so very much for your time and for this really inspiring talk. And I really hope that this webinar has been informative for all the participants and also inspired them. Um, okay, in that case, we can call it off today's session.
Thank you. Thank you, Sonia. Thanks, everyone. Bye.
Bye bye.